So last time we did the rules for differentiation, and the main thing was the product rule and the quotient rule, and that's where we ended off at. We worked this example, and we found the slope of the tangent line. We found the derivative to this function at that particular value. On the next slide, it's just algebra, taking that question one step further. So let's just remember that the slope of the tangent line, the derivative at 1 was -1/2. So on the next slide, we want to know, well, let's go ahead and find the entire equation of the tangent line. All right. The tangent line has the slope that we know is -1/2. Slope of the tangent line is the derivative at that particular x value that we're interested in. It's the same x value from what we calculated on the last slide. So the derivative at 1 was -1/2 from the last slide. So that's going to be your m. You have your m. And then we're going to plug into this formula, y equals mx plus b. You also have your x and y. The point of tangency is the x and the y. Now that you know your m, you can just go get what b is by plugging in. Tell me, what is it? Yeah, we'll call it 5/2. We'll call it 5/2. All right, great. So then that's the equation of the line. And here's what the graph would look like. That curve and that line, tangent, we found the equation. There's another line that we need to be aware of. It's called the normal line. And basically, the idea is that the normal line is perpendicular to the tangent line. At that point of tangency, not just at any point. At the point of tangency, there's a line that is perpendicular to the tangent line, and we call that line the normal line. What do you know about perpendicular lines? How do their slopes relate to each other? Okay, so if our slope is -1/2, what's the opposite reciprocal? +2. So that is the slope of the normal line, opposite and reciprocal. So do the same algebra with the x equals 1 and the y equals 2, but now the m is 2. And so what is that? 2 equals 2 plus b. I guess b is 0 then. Yeah, b is 0. So the normal line, and it ends up going through the origin, it's y equals 2x. And here's both of them drawn on the same graph. So if anybody ever asks something about a normal line to a curve, they mean a line that's perpendicular to the tangent line at the point of tangency. Okay? Questions on that? Good with that? All right, great. Sometimes the question might be asked in an abstract kind of way. We don't have the formula for f of x and g of x like we did before. And so now we have to still be able to answer the question. I'm going to make this new function up from f and g by dividing f by g. Call it q. And I'm interested in q's derivative at 7. And all I have is f's graph and g's graph. Okay? So since q is this quotient, then we'll use the quotient rule, where we square the denominator, we bring the denominator up to the numerator, we take times the derivative of the numerator, then we subtract the derivative of the denominator times the numerator. And we're interested in this at 7, so every place we see an x, we're going to replace it with the 7. The issue is, how do we go and get these values? We have 4 different values, actually. There's both the f and g at 7, and the f prime and the g prime at 7. And the issue with this problem is, how do you get them off the graph? Let's start with the easier ones. How do you get f of 7? Just from looking at the graph. You see what the y is when x is 7? Okay, so each tick mark is 1. So we go over 1. Let me put these in here. 4, 5, 6, and 7. So what's the y value on when x is 7, what's the y value for f? 5. So f of 7 is 5. Great. What about g of 7? 1. Great. So we're just reading off how tall it is off the y-axis, off the x-axis. Great. Now, how about the derivative? Remember, the derivative is the slope of the tangent line. If your function is linear, then the tangent line and the function are alike. They're exactly the same. So at x equals 7, there's no difference in the tangent line slope and the line, which is the function. They both are linear. If we would have had to find the slope of the tangent line on this parabolic part, then that would be difficult to do by eyeballing it. But as far as a linear part, we can tell the slope of a line. And so what g prime of 7 and f prime of 7 are, they represent the slope of these lines. I have this line here. I need the slope. And I have this line here. I need the slope because that line is the tangent line. So how do we find the slope of a line just by eyeballing the graph? How can we tell what the slope is? What is slope anyway? Changing y over changing x. Okay, rise over run. If you can find corners that the line go through, then it'll be easier. It doesn't have to always go through corners, but if it does, take advantage of that. Because then it'll be an integer change in y and an integer change in x. And so here are two corners that g go through. Here are two corners that f goes through. And we can see the rise over run. There's a triangle there. And we can eyeball the rise over run. Only because it's a line. Now, had this been the parabolic part, then it would be much more difficult. So for f, what is f prime at 7? What is the rise over run? There. What's the rise? 1. What's the run? 4. So the slope is 1/4. And that's the tangent line slope. How about g? You don't rise, you actually fall. You go down 2, and you go over 3. The run is 3. So negative 2/3. Very good. All right, now you have all the players in the formula. Go plug them in. You have f prime of 7 supposed to be multiplied by g of 7. So I got this guy here, and I'm supposed to multiply by this guy. And then I have f of 7, I'm supposed to multiply by g prime of 7 with a subtraction sign in between. And thankfully, the denominator would just be 1 squared. Okay, so be able to answer this question, first show that you know how to use the quotient rule, and then show you know what these symbols really mean, because you don't have the formulas, you just have graphs. Okay, it's a 4 plus 10/3, or 1/4 plus 10/3, common denominator 12. So 3/12 and 40/12. So altogether 43/12. All right, be able to answer a question like that. Let's see something here. Let me discard that. The next slide, I think I want to skip in the interest of time. Let me see what this next slide is. Oh, no, we'll do the next slide. There's one slide I want to skip. Yeah, that slide there we're going to have to skip in the interest of time. All right, let's do this next slide here, and then we'll see how we're doing. Today we want to get through this and the next section, which is not 3-4. We're going to come back to 3-4. The next section is going to be the trig derivatives. So we did this one already. Let's go to the next one. Okay. Find the point on the curve where the tangent line is horizontal. Okay. This is a cubic function, and we want to know where the tangent line is horizontal. What does that mean? What do you know about a line that's horizontal? 0 is slope. Okay, slope of the tangent line is 0. Slope of the tangent line is the derivative. So you're asking yourself, where's the derivative 0? All right, great. So what's the derivative? Use the power rule on each of the individual terms. you should be able to just to look at it and eyeball and just quickly spit out what the derivative is. If that's your function, what's your derivative? First term is 6x squared. Second term? 6x. And third term? Minus 12. Okay, great. Now you want to know where it's equal to 0 at. You have to find the x that make it 0. Algebra now. Calculus over. It's a quadratic.
Set it equal to 0.
Set it equal to 0 and factor if you can. If you can't factor, then what do? You have to use the quadratic formula. We're trying to keep it to, quadratic, or if it goes higher, maybe there's some trig, maybe some other, maybe this could be difficult. And so if it is higher, then maybe, we could do something to help us out with the factoring. But in most cases, I would like for it to be able to be factorable. You should try to think that it is factorable. I want you to be able to make it through the problem without having to rely on the quadratic formula. But if you can't, if you have trouble factoring, then you can always do the quadratic formula. Something that you can take advantage of, though, is the fact that you see the coefficients are 6 and 6 and 12. Take advantage of that. Factor out what they have in common. Therefore, you're dealing with smaller numbers. There'll be less combinations when it comes time to factor it. So take the 6 out. When you take it out, you're left with x squared plus x minus 2. And you'd much rather factor that than the previous. Because you only have like 2 options with this, but you had so many different options with the other. When you can, factor out. And so we have to factor x squared plus x minus 2. How does that factor?
X plus 2, x minus 1.
Plus 2 and minus 1. And then you're interested in knowing where it's 0. It's not the 6 that's 0. It's either the x plus 2 that's 0 or the x minus 1 that's 0. So you can't just say the answer is 2 and 1 or negative, or I guess 2 and negative 1. You can't just say that. You take these separately and set them equal to 0, and you get the opposite signs. You get negative 2 and positive 1. Okay, and that's almost your answer. That's the x values. Go back to the question carefully. It says the points on the curve. So you haven't given them everything they want. You have half the value, basically. A point is an x and a y. X comma y, coordinates, right? So we have the x. We need the y. How do we get it? To where? Not the derivative. We know it makes the derivative 0. It's not that. We want the y, right? I have the x. I want the y. Go back into y. Go back into f of x. So plug a 1 in to the original function. Plug a negative 2 in to the original function. Negative 2 is a little bit more difficult because of the fact that when you cube it, it's negative. So we're going to have the first term actually be a negative 16. And then the second term will be a positive 12. And then a positive 24 and a positive 1. All right. So what's the y value there? 36, take away 16 is 20, I guess 21? 21. Great. All right, well, plugging in 1 is a whole lot easier because you just take the coefficients, really, right? So 2 plus 3 minus 12 plus 1. So that's a whole lot easier, algebraically at least. And that's what? Negative 1. What's that value? Negative 6. Okay? You're done. That's what they were looking for. The points. Here's the picture. You're looking for those horizontal tangent lines, places where the tangent line is 0 at. Slope of the tangent line is 0. All right, great. I'll be able to answer these kinds of questions. Your next homework assignment has that on it. Let's see here. All right, one more of these, and then we'll change gears. Here's another quotient function: x minus 1 over x plus 1. Okay, and so I want to know places where the tangent, there's going to be multiple tangent lines to this function. I like to know the equation of the tangent lines to this curve that happen to be parallel to this other line. And the other line isn't given to you in some standard y equals mx plus b form, where you can easily tell what the slope is. And so we can just solve it though, and put it in that form, and find out that the slope of that line is a half. You would like for your tangent line to have the same slope, right? Parallel line, same slope. So last time we were taking the derivative and setting it equal to 0, because we're looking for horizontal sloping tangent lines, horizontal lines for your tangent. Now we're looking for the tangent line to be, the slope of it, to be equal to a half. So when we take our derivative, instead of setting it equal to 0, we're going to be setting it equal to a half. But this time the derivative is a lot more work. Last time we just did the power rule, we were able to spit out the derivative in no time flat. Now we need to work through the quotient rule to get the derivative. Okay, so we need the same slope. We need our tangent line to have the slope of a half. All right, let's work the quotient rule. Let me actually work it out here. Quotient rule. How does that work? We have to square the denominator. So the derivative is take the denominator and square it. Take the denominator and bring it up to the numerator. Then multiply it by the derivative of the numerator. What is x minus 1's derivative? Just a 1. It's mx plus b, and just the coefficient on x is the derivative. Put a minus sign, reverse that process, leave the numerator alone, and multiply by the derivative of the denominator, which is also 1. All right, great. So we have that, and then we need to simplify this. There's nothing to plug in. Like in most cases, we're trying to plug something into this, but now it's backwards. We know what it's equal to, and we have to solve for the x. So we need to simplify it. This numerator isn't as bad as it looks. It's x plus 1, now be careful here, minus x plus another 1. So your x's canceled. And you're left with 2. That is your derivative. You like for that to be equal to a half. And now it's algebra. Solve for x. Right? It would be parallel to that line if its slope was a half. And it can happen more than once. So that's why they say lines. There's going to be more than one. I don't really care about the equation. Let's just see where the x is. We can stop right there. I mean, the equation part, that's just some basic algebra that we've been doing already. So where is this equal to a half? Let's do this part. And we can just move on with it. Where is this equal to a half? How can we solve that? Fraction equal to a fraction? Cross multiply. Okay? So 4 should be equal to the quantity of x plus 1 squared. If you go and multiply this out, x plus 1 squared, you're making life a little more difficult than it should be. It's already a nice perfect square, so take the square root. Your job is to get inside to that x. It's already nice and factored in this nice perfect square. So square root both sides. Don't multiply it out and then you could get it that way. Multiply it out and then set it equal to 0 and factor that quadratic. I mean, that would work. But when it's a nice perfect square equal to some number, take the square root. And don't forget, it'll be on the other side, plus or minus. Not just 2, but plus or minus 2. Basically, what's on the inside, right? X plus 1. Either could be 2, so it squares to 4. Or that x plus 1 could be minus 2, so it squares to 4. And so either x plus 1 is 2 or minus 2. Let's just solve that and be done with this. Although the question asks us to go further. So either x is 1 or x is negative 3. Okay, there's some more steps to it, but this is the big picture. This is the heart of the matter. Finding these x values where you have a tangent line slope of a half. Okay, I'll show you the rest of it, and it's not that complex. So we have the 2 and the, where's it at? We have the negative 3 and the 1. You go get the lines, and that's what the picture looks like. Sorry about that. Let me blow it up again. You solve it, and you get these values here, 1, and you find a tangent line there. You go to get the, with -3, you go get the tangent line there, and then and that's what the graph looks like. The slope of those lines are half. They are parallel to that other line in the original statement of the problem. Okay? All right. Good job. Questions on that? Yes? When you find a derivative, what exactly is that? In terms of the problem. When you find a derivative, what is the derivative? Okay? This is the one question that you have to be able to know the answer to in this class. Okay? The slope of the tangent line slope is the derivative. And so, when you find a derivative, this formula here for the derivative, when you go and find that, it is the slope of the tangent line. This represents the slope of the tangent line. And that's why we set it equal to a half, because I want my tangent line to have that slope of a half. So, if you get nothing else out of this class, you're going to walk away knowing that the derivative represents the slope of the tangent line. Okay. All right, good. I have to skip the next slide in the interest of time. It's okay though. You can look it over, and if you have any questions, it's already. I think this is already posted. Yeah, 3.3 is already posted. But this one I don't want to skip. This one's important. Remember how we had the piecewise defined function, and we asked the question, is it continuous? Well, we can also take those kinds of functions and ask the question, is it differentiable? What does differentiable mean? Does the derivative exist? Continuous, what does that mean? Is it broken? Okay, so this isn't the continuous question. This is the does the derivative exist question. Okay, if you ever see that word, don't be intimidated by that word. All it means is, does the derivative exist? Is it differentiable? Does the derivative exist? Now, is there a derivative at 1? Now, what type of ways can you not have a derivative? We had a picture with 3 different, we had a slide with 3 different pictures on it. And we said there's some different ways where the derivative might not exist or won't exist at all. What are those 3 different ways? A cusp, any kind of sharp point, be it 2 curves meeting up in a sharp point or 2 lines meeting up in a sharp point. If this happens here, if our 2 parts meet up in a sharp point, then we don't have a derivative at that value, x equals 1. What else was the other type of ways that you could not have a derivative? A jump, where your function's going one place, and then on the other side you're going to some other place. That's a jump discontinuity. You can't have a derivative at that point. So if we knew what our function did, we can answer this question. So let's do that. Let's see if our function, first, if our function isn't continuous, right? If there's that jump, we stop right there. It's done. The answer to this question is no. So let's see if there's a jump. How do we do that? We see if the left hand is going to the right hand. They're going to the same place. All right? So, we just care about the point where the function is supposedly broken at x equals 1. We just care about that. So at x equals 1, here we go. On the one hand, I'm 2 minus x, but on the right hand, I'm x squared minus 2x. Is that plus? Yeah, plus 2. So basically, I'm looking at a line meeting up to a parabola. Generally, that's probably going to be at a sharp point. Maybe it's possible for the line to meet up to the parabola in a smooth point. Another thing about differentiable when you're looking at the graph is that it's smooth. There's no sharpness to it. And so maybe it's possible to have the line meet the parabola and be smooth. If so, the answer is yes. But if not smooth, if it's sharp or not together, then the answer is no. And so first off, let's just make sure it's together. Let's answer that question first. Is it together? Is the line going to the same place that the parabola is going to? Okay. The left-hand limit would be using the line. The limit as we go towards 1 from the left is using the line, and the line is headed towards? What's this limit? Where's the line headed towards when the x is 1? Okay, good. 1. Wonderful. What's the parabola heading towards? Plug a 1 into that. If all goes well, we get a 1. Right? True? Okay, great. So we at least know that they're headed to the same place. Okay, there's no jump. Okay? But they could meet up sharp. It's very possible. You know, it's going to be very rare that we can have them meet up and not be sharp. So you just think about the whole aspect of a line meeting with a parabola. How could that possibly not be sharp? And so it's possible, but it'd be rare if it was. How will we know if it's sharp or not? The whole thing about being sharp, I'm sorry, questions? Your hand was first. Yes, that's what we need. The derivatives to be equal. My slope going in better equal my slope going out for me to be smooth. See, when you are sharp, if your graph has a sharp point in it, they don't even have the same line. Your tangent line slope going in is positive and your tangent line slope going out is negative, or vice versa, when you have a sharp point. So that's what we need to focus on then, the derivative, and see if they meet up. If the functions meet up and the derivative parts meet up, then the answer is yes, it is smooth. Okay, I don't think that's going to happen here though. But let's take a check. So all we can answer here is yes, the function is continuous. Now we need to check the derivative. If you have one of these kinds of functions, how do you take the derivative? You take it in parts, right? The derivative, if it is supposed to exist, the derivative on the left-hand side would be what value? This line has a slope of -1. Lines have the same slope as their tangent lines. Great. How about the parabola? I'm sorry, I wrote over it. Let me erase this thing here. What about the parabola? What's the derivative there? 2x minus 2. Okay, and we're interested in what's going on at 1. Okay, so when you have this question, a piecewise function, is it differentiable? First check this. If the answer is no, then you're done. And now check this. If the answer is no, then you're done. But if the answer is yes, you're also done. The answer is yes to the question. Yes, it's differentiable. And no, right? At 1, these guys don't meet up. At 1, if we can go back to this kind of thing, at 1, this one's stuck on -1 regardless. But this right-hand side obeys the line 2x minus 2. So your left-hand limit here will just be -1, but your right-hand limit here will be what? At 1. It'll be 0. So you're coming in at a slope of -1. You're going out at a slope of 0. Sharp. Okay, I'll show you what the picture looks like and everything. That's the heart of the matter, okay? So piecewise differentiable, you have one of the very first question on your next hand-in homework is this question. Okay? What? Maybe it's a and B solve for constants, but yeah, this is what you need. Continuity on the function meeting up, and basically take the derivative and make sure it meets up. That's the heart of the matter. What I have typed on the slide basically says that, but nothing says it better than what we have right here, right now. That captures everything.
Wouldn't you just be able to try to find the derivative, like instead of doing the first step, just skip the second step?
No, it's possible for the second step to have a yes, but the first step to have a no. In some way, I can cook up a problem that does that. So you need the first step before you can go to the second step. And so what's so good about the first step is when the answer is no, you're done right away and you don't even need a second step. But you got to do the first step first. Make sure the function meet up. Make sure the left-hand side is going to the same place that the right-hand side is going to. Okay? So step 1 is this. Do it for the function. And step 2 is this. Do it for the derivative. All right, great. I don't know what I have typed, but it's not that clear, I'm sure. Yeah, I mean, it's a bunch of words, but I think it's saying the same thing. And here's what the picture looks like, just so you know. Sharp. Coming in at a slope of -1, going out at a slope of 0. Okay? And here's the graph of the derivative of such a function. So the answer is no, is not differentiable. Okay? All right. Raise your hand, be honest, if you watched the squeeze theorem video. Yeah? Oh, good. In that video, I went through a bunch of slides just talking about why we should care so much about the squeeze theorem, and the bottom line is the main reason is when it comes time to look at trig derivatives, there are two limits that come into play, and we want the ability to be able to say that one of these limits is 1 and the other limit is 0. And so if you want to know why, you're going to have to go back to the squeeze theorem video on our webpage to see how I went about doing that. I proved both of these guys in that and the reason why I guess I have it here too, but I'm not going to go through it. I'm going to just instead of just telling you that sine has cosine as its derivative, we're going to walk through the definition of it and see why sine has cosine as its derivative. I would never have you derive this anyway. I'm just going to have you use it, of course. But the definition of the derivative is that the limit of the secant line slope is a tangent line slope, and you're letting h go to 0. And so, but when you actually have to go and do it, there's an issue because we're talking about the sine of x plus h. And we have to subtract from that the sine of x. In order to do that, we're going to need this identity. It comes out of nowhere. The sine of an angle sum is equal to the sine of one times the cosine of the other, and then you reverse that and put a plus sign, plus the cosine of the first times the sine of the other. Anyway, that identity comes out of nowhere, and we need it to prove that sine has cosine as its derivative. Okay? Not that I would even have you put that identity on your cheat sheet. It's an obscure identity when it comes time for trig identities. I mean, you got to know the ones with the squares, like sine squared plus cosine squared is 1, and less often used is 1 plus tan squared is secant squared. We need to know that too. But I wouldn't say you need to know the cosecant cotangent version of that. But the fact that the sine of twice x is 2 times the sine x of cosine, basic identities that you can find in your textbook. This was not a basic identity. I don't want this on your cheat sheet. You don't have to worry about this. I would not have you using this. I just need to employ it to help me show you that sine has cosine as its derivative. In our numerator, that's going to be the first half of the numerator. It's going to replace f of x plus h. I'm going to factor out what they have in common. I'm going to take the first term and the third term. They both have a sine x in them. And so I'm going to put them together and factor out that sine x. Okay with that? And then what I'm going to do is break this into 2 separate fractions where the right-hand side is over h and the left-hand side is over h, and there's a plus sign in between. The limit of a sum is the sum of the limits. So we could do that. Okay? My limit is as h goes to 0. So anything that has just an x in it plays no role. And so it's going to be basically pulled out of the limit. We can pull the sine x out of the first limit and pull the cosine x out of the second limit and focus on these h limits. These are the 2 limits that I went through and proved in the squeeze theorem. This first one doesn't require a squeeze theorem, but the second one does. In that, it's not even long. I think it's like maybe 25 minutes at the most, maybe 30 minutes. It's a short video, but you need it. And so here's where we use it at. The first limit is 0, while the second limit is 1. And so the derivative would be 0 times sine and 1 times cosine. So that's why sine has cosine as its derivative. Okay. But then you always wonder, well, why doesn't cosine have sine as its derivative? It's a different formula. This summation form, the sum of the angles formula. This sum of the angles formula is different for cosine of x plus h. Okay, and so we'll see that a negative comes in there, and that's why cosine has sine as its derivative. Here it is here, worked out for you. I'll just do it real quick. Please don't write it down. Just sort of pay attention. Same idea, and here's the reason. This trig identity has a minus while the other guy had a plus, and the cosines are together and the sines are together. So when you go through the same mechanics of plugging this in for the left-hand part of the numerator, and then taking the two parts that have cosine and putting them together and factoring that out, splitting it into two separate fractions, factoring out the x parts and having those same two limits, we get the 0 and the 1. It's the minus sign. I put it in red so it stands out. It doesn't really look like it stands out. But that's why cosine has negative sine x as its derivative. Okay. And those are the main two. Everything else comes from that. I mean, I'm gonna show you how you get tangent, but you don't have to derive these things. Just know that sine's derivative is cosine, and cosine's derivative is negative sine, and then basically tan. Those other guys you can just put in a cheat sheet, the reciprocal guys. They all can be derived, but in the interest of time, I'm not going to derive all 6. I derive these 2, and I'm going to derive tan, but I'm not going to derive the reciprocal guys. But you could definitely do it. Just take a look at how we derive tan, and that will give you an idea on how you're going to derive the reciprocal guys. What is tan? It's all based on sine and cosine. All the other 4 trig functions are some kind of relationship between sine and cosine, or maybe just one of them. And so tan is the sine over cosine. So I'm going to do the derivative of tan by knowing the derivative of sine and cosine. I'm going to do the quotient rule, where I take the denominator and square it. Okay. I take the denominator and bring it up to the numerator. So I take the cosine and square it. I'm going to write it like this. I'm going to take the denominator, bring it up to the numerator. I'm finding the derivative here. And then I'm going to multiply by the derivative of the numerator, which is cosine. Then I'm going to put a minus sign. And then I'm going to leave the numerator alone and multiply by the derivative of the denominator, which is -1 times the sine. And what happens is you'll get a cosine squared. I'll put it there for some reason. And then minus on minus, you get sine squared with the plus in between. And so that's just a fancy way of saying 1. The numerator is just a 1. So your derivative of tangent is 1 over cosine squared. Okay. I like it like that. But in most places, you'll see this called secant squared. Right? The reciprocal of cosine is secant. So we're going to have a chart that'll have all 6 of our derivatives. And from here, you're just going to go and use them. Okay. So, sorry, I have it here on the slides. So here's our 6 guys. Sine has cosine as its derivative. Cosine has negative sine as its derivative. And tangent has secant squared. Okay, if you wanted to, you can figure out these other guys, but here they are. What's the reciprocal of sine? It's cosecant. Okay, and it has the following as its derivative: negative cosecant x times cotangent x. You can show that if you want by doing the reciprocal on sine. The reciprocal of cosine is secant, and it has secant x times tan x. And whatever you need to do to memorize, I would say don't even worry about memorizing, just put them on your cheat sheet. But there's a way you could probably make your way through that. And cotangent has negative cosecant squared. All right, so it's 36 things on your 36 functions and derivatives on your cheat sheet. If I ask you something that involves these, you'll be ready to now go and just use it and not have to worry about what was tan's derivative again and have to go through all that work you just did up top. You don't have time for that on the exam. Okay? All right. So here's a question. I have this function, sine of x times cosine x. And it's the same question that we had before. Show me where the tangent line is horizontal. So tangent line horizontal means that the slope of the tangent line is 0. So we take the derivative and we set it equal to 0. But this time we're using trig, a little more difficult. Okay, sine x times cosine x, product rule. You ready? Derivative of the first times the second. So cosine x times the cosine x. This guy would be the derivative of the first and then times the second. Put a plus sign. Take the derivative of the second and multiply it by the first. The derivative of the second is negative sine x. So this time, if you don't get a 1, you get cosine squared minus sine squared. That's your derivative. If you want to know where that tangent line is horizontal, that means the slope of it is 0, but we know the slope of it is the derivative, so we set this equal to 0. We have to solve this trig equation. That's why we spent time on it on the first couple of days of class. We have to find the x. Technically, when you solve trig, there's infinitely many answers. We're only interested, though, in the answers that fit in the range of values from 0 to 2 pi. All right. Suggestions? Yes. I'm sorry, what's your name? I gotta know names. So if ever you raise your hand, I forget to ask your name. Please just tell me your name so I can. This is a small enough class. I need to know everyone's name. Allison. Okay.
You can use the identity to sort x plus sine squared x equals 1. Or, yeah. And then
So use identity that the cosine squared plus the sine squared is 1. So it is true that we used it earlier. Cosine squared plus the sine squared is definitely 1. Could we use that here somehow? I mean, I guess we could somehow.
like, make the squared x equal.
Instead of having both cosine squared and sine squared, trade one of them in for the other one? Nothing wrong with that. Which one do you want to trade?
The sine squared, or the 1 minus sine squared x squared.
Okay, so cosine squared is definitely equal to 1 minus sine squared. Nothing wrong with this attack. I mean, what else are you going to do? That's what you think of, right? Just do what you think of. So she's saying, I want to replace it. So I'm going to replace this cosine squared with 1 minus sine squared. Here's another minus sine squared. It's supposed to be equal to 0. Okay, nothing wrong with that. Let's put them together. Why have two of them separate like this? So 1 minus 2 times the sine squared should be equal to 0. Nothing wrong with this attack. Maybe it's not what you thought, or there's actually 4 or 5 different ways you could have went with that. Nothing wrong with that. Do it the way you want to do it and see if you get the same answer that we get. Okay? What we're going to do is solve this for x. We need to subtract the 1 and divide by the negative 2. We'll have negative 2 sine squared x equals to negative 1 divided by negative 2. So where does the sine on x quantity squared equal to a half? Take the square root. Where does the sine x, or when you take the square root, don't forget, plus or minus. Gotta have the plus or minus. So where does sine x equal the positive root of a half and the negative root of a half? That's not really a mystery. That's our friend root 2 over 2. Right? The root of a half is the root of 1 over the root of 2. It's 1 over root 2. Rationalize. It's root 2 over 2. Right? That comes from the 45s, right? You got to remember what quadrant you're in, whether it's positive or negative. But yeah, we're going to get our 4 versions of 45, right? So sine x equals root 2 over 2. There's 2 places where that happens at. Sine x equal negative root 2 over 2. There's 2 x values where that happened at. In this range of 0 to 2 pi. Just think of the unit circle. Unit circle. We're talking about these 45s here. And we need them. That's all. Okay. For pi over 4, for the first 45, it's positive. This is x equals pi over 4. For this next one, the sign is still positive. Sign is negative when the y is negative, right? The y value on the unit circle corresponds to sign. So it's 3 pi over 4 is what that one's called. And then these two down here are 5 and 7 pi over 4. Okay, so it can get a little messy if you're not used to solving trig equations. We have to pull identities. Just keep the set of identities that you pull from small. I mean, this isn't the only identity we could have pulled, but it worked. So just go with it. And if you try something else, just make sure you get the same answers. And remember that we're only focused on answers in the first revolution from 0 to 2 pi. Okay, so those are the answers to the question. And I think I have a graph underneath here, but sometimes I just don't like to go with all the animation. Sometimes I just like to write it out. And so I'm sure what I wrote out looks very different than this, but in the end, it's the same answer. Okay. How are we doing on time? Is that clock right? Wow. This whole class just went by so fast. Yeah, I even put the unit circle in there. Yeah. Oh, I did a, let me just show you what I did. I did a difference of squares. See that? Cosine squared minus sine squared. I did, a squared minus b squared is a plus b, a minus b. It works too. That's fine. Either way. And here's the graph. And the, oops. Wow, what happened there? And here's the graph. And those 4 places were where you would have a 0 sloping tangent line at. 1, 2, 3, 4. Horizontal tangent line. 46. We can't really do any more. Let's save the rest of this for Monday. Monday we'll finish this, and we got to talk about the chain rule. That's the last new subject before the exam. The chain rule. It's in section 3.6. Okay. Wednesday we'll have just a whole day of review. Ask lots of questions, and we'll go from there.